Bismillahirrahmanirrahim. Assalamu alaikum. I'm Dr. Farhad Ali, your instructor for the course of partial differential equations. I hope you will have this lecture in very good health. This is the 13th online lecture, and you will have this lecture. You can find this lecture in the 14th week. In the previous lecture, we have found some Laplace transform of some elementary functions. In this lecture, you will see that we will have to find some Laplace of some functions, some special function, as well as some techniques and some theorems, which will help you to find the Laplace transform. You can see here I have this theorem, initial value theorem. The statement of this theorem is if f of t and f dash of t are Laplace transformable, means you can find the Laplace transform of this. It is a piecewise and continuous and exponential order function. The same, this function is also continuous and of exponential order. This is called the Laplace transformable. If this is the condition, if f of t and f dash of t are Laplace transformable, and f of this is the Laplace transform of f of t, and the Laplace of this f of t is fs. Fs is the Laplace transform of f of t, then the behavior of f of t in the neighborhood of t equal to 0 means the function in t plane, the behavior of the function in t plane at time t equal to 0 corresponds to are the same as f of s. This is s, correspond to the behavior of f of s in the neighborhood of s tends to infinity. So this is, you have to clear this statement first. That is, we have function f of t, and then we have function f dash of t, because the Laplace of this, you will see that of the first derivative, this is ordinary differential equation d f of dt, f dash of t. Yes, we have these two functions, f of t and f dash of t. This is the function, and this is the first derivative of this function, and they are Laplace transformable. And we know, and this is also f of s is the Laplace transform of f of t, then the behavior of f of t in the neighborhood of t equal to 0, or the response of this function at t is equal to 0 will be equal to the response of sf of s in the s plane in the neighborhood of s tends to infinity or is equal to infinity. So in the t plane, the behavior of this function in a t, the f of t at t is equal to 0 will be same when we take the Laplace of the first derivative s of s in the neighborhood of s tends to infinity. So when we take, or when we let s tends to infinity and this function in the s plane after the Laplace transformation, it will be the same when we put t is equal to 0 in this function. So they will have the same result. And this mathematically, what does it mean? That the Laplace transform limit t tends to infinity, when we put t equal to infinity in this function of t, this will be equal to, in a transform form, that these two relation will be same, or their response will be same when we in the s plane when we s tends to infinity. Okay, in this function f of t when t is equal to 0 will have the same response, and when we transform this into s plane and then we put s tends to infinity, so they will have the same response. So we have the proof of this theorem. From the property of the derivative, we have we will do this. So far we didn't take the Laplace of the derivative. So in maybe in some lecture we will have the Laplace of the derivative. Okay, so the Laplace of dy by dt or df by dt, first derivative. F dash of t means dy by dt. Any function which is uh, can be differentiated with respect to time. Ordinary differential equation, only the function of one variable, one independent variable. So, and that independent variable will be t. So when we take the Laplace transform of the dy by dt or df by dt, so it will be s f of s minus f of 0. So this is the formula. The Laplace of the first derivative on the differential equation. The first derivative is with respect to time is s f of s minus f of 0. Okay, so this is the Laplace of f dash of t. Now taking the limit s tends to infinity on both sides, we get, and you know this is the Laplace of f dash of t. So let me put this in by definition. Limit s tends to infinity, 0 to infinity, e power minus st f dash of t, because we are going to find the Laplace transform of f dash of t dt. Limit s tends to infinity, sf of s. Okay, and the Laplace of this, when you open this integral, you will have sf of s minus f of 0, and we have taken this limit on both sides. We have let uh, this limit s tends to infinity. So limit s tends to infinity is f of s minus limit s tends to infinity f of 0, but this is t actually, f of t. Okay, so 0 to infinity, and we can bring this limit inside the integral as with respect to s, this is constant dt. So limit s tends to infinity, e power minus st f of t dt, limit s tends to infinity is f of s and minus f of 0. So when you apply limit, you can see when s tends to infinity, so we can replace this s by infinity. So e power minus infinity is equal to 0. E power minus infinity equal to 0. So this term will make this whole term equal to 0. Limit s tends to infinity is f of s minus f of 0, and limit s tends to infinity. Okay, so we can bring this to the left hand side. So this will be equal to limits, and this is f of 0, but this is f of t, because f, when we take the Laplace, so we denote this from the capital F. Okay, so if you look at this one, that the Laplace of f dash of t is equal to s f of s minus f of t at t is equal to 0. So that's why I have put here f of 0, because this is f of t, but t is at t is equal to 0. So as there is no s, so this limit will not be applied on this, because this is f of 0 means f of t. So I can write this, I just I shifted this to the left hand side, and limit f of t tends to 0, because this is f of 0, both are same. Just I have put here, instead of 0 I have put t, and t tends to 0, because this is t. Okay, and f of 0 means f of t, and t at t is equal to 0, and limit s tends to infinity is f of s. So both are same. You can see this is the theorem says that this term at t is equal to 0 and this term at s tends to infinity, both are same, both have the same response. So we have proved this. This is, we are given to prove this one, this relation. limit t tends to 0 f of t, limit is f of s tends to infinity. So already we have proved this one, and we call this initial value theorem. So now we have example. Uh, Let f of t be a polynomial of degree n of the form. So we are just going to verify this theorem by taking an example. F of t equal to a naught plus a1t plus a2t square and plus a n tn. So Laplace of f of t is Laplace of this is equal to taking the Laplace on both sides. So the Laplace of this function will be equal to f of s, and you can see the Laplace of a naught is a naught I is a1t. So the t Laplace is 1 by s square, and a1 is constant, and the Laplace of t square is 1 by s cube, a2 is constant, and similarly the Laplace of t power n is n factorial divided by Sn plus 1. It has been proved. So now we can write S f of s. We multiplied both the equation with S f of s. So you can see here when we multiply S f of s, a naught of s, a1 of s square, you can see here a naught s will be cancelled, and this will become a1 by s, and 1 we have multiplied s, so s will be cancelled with 1s, so we will have 1 by s square plus n, and n factorial is n only because we have multiplied 1, so it will become s minus 1, so that we will have n factorial divided by Sn. So you can see S f of s, now taking the limit as s tends to infinity on both sides. So limit s of s tends to infinity, and s tends to infinity means 1 by infinity, and 1 by infinity is equal to 0, 1 by infinity square is equal to 0, and 1 by infinity n equal to 0. So just we have a naught. Limit s of s tends to infinity a naught. So in the s plane, when we let s tends to infinity, our result is a naught. Now in t plane, before to change this to Laplace in t plane, and when we put t equal to 0, so what will be the response? Limit t tends to 0. When you put here, you can see that we have, now taking the limit as t tends to 0 in the original function t, we have limits f of t at t is equal to 0, we have a naught. So it's quite clear from this one, when t is equal to 0, so just we have f of limit f of t when t tends to 0, we have a naught. So what does it mean? That s f of s when s tends to infinity have the same value a naught, and when we put t equal to 0 in the original function, so this implies that limit s tends to infinity s f of s, limit f of t equal to 0. So both are same, both have the same behavior. So this is the proof from a mathematical example of the initial value problem, initial value theorem. This is the final value theorem. Another theorem, the first one is initial value theorem, this is the final value theorem. If f of t and f dash of t are Laplace transformable, the same statement, and f of s is the Laplace transform of f of t, then the behavior of f of t in the neighborhood of t tends to infinity, just we have changed the limit from t0 to 2 infinity, corresponds to the behavior of s f of s in the neighborhood of s equal to 0 instead of s tends to infinity. So we change the limit as compared to the previous one, the initial value theorem. T equal to 0 change to t infinity, and s is equal to infinity change to s equal to 0. Mathematically, limits f of t tends to infinity equal to limit s equal to 0 s f of s. So we have to prove. In the initial value theorem, we have here 0 and here infinity, but now we have changed this. This is from 0 to infinity, and this is from infinity to 0. So again, from the property of the derivative, we have Laplace of f of dash t is equal to s is equal to s f of s minus f of t at t equal to 0. This is the Laplace of the first derivative with respect to time. S f of s minus f of t at t is equal to 0. So that's why I have written only 0, f of 0. This is t. So by definition, the Laplace f dash of t can be written as 0 to infinity e power minus st from f dash of t equal to dt, and which is equal to these things. Taking limit s is equal to 0 on both sides, look at here, this is 0 to infinity f dash of t ft. So you can see because if you solve this one, so we have d will be cancelled to the first derivative will be changed to, if you take the integral of f dash of t, so it will become f d. This dash will be cancelled with this, okay, and just we will have f of t 0 to infinity, okay, and limit s tends to 0, we have s f of s minus f of 0, because we have taken x equal to 0 on both sides. So how f dash t becomes, because when you take x equal to 0, so by putting x equal to 0 here, this term will become 1. So just we will have f dash of t dt. Okay, by putting the limit, the above this relation, when s is 0, so you can see e power 0 multiply t e power 0, and e power 0 is equal to 1. So we have only 0 to infinity f dash of t dt. The integral of f dash of t is f of t, and the range are 0 to infinity. The limits are 0 to infinity. So apply the limits. Upper limit, which is already written, is a limit f of t when t tends to infinity. This is infinity, and minus lower limit f of 0. Upper limit minus lower limit, and limit s f of s tends to 0. So you can see we have f of minus f of 0 here, and also minus f of 0. So we can cancel f of 0 and f of 0, both are same function with the same sign, and they are one is on left hand side and one is on the right hand side, so it will cancel each other, and sorry, this is infinity, okay, limits tends to infinity. So let me write here this one. This is infinity, and this is also infinity. Okay, so limits t tends to infinity, f of t is equal to limit s f of s at s is equal to 0. So this is the final value theorem, and it has been proved. Uh, now we have another theorem division by t. When a function is we have that when t is multiplied with a function, so what will be the Laplace? And we know this, that is minus 1 power n dns by ds dn by dsn of the f of s. So now theorem states that if Laplace of f of t is fs, we know that the Laplace of f of t is fs. Okay, after this operator, when you apply this operator Laplace, f of t will be changed to from t plane to s plane, f of s. Then the Laplace of f of t divided by t, if the function is divided by t, then the Laplace will be from s to infinity f of s ds. So this will be formula direct how to find if a function is divided by t. So then it will, the limit will be start from s to infinity f of s ds. So we can apply this formula, okay, to find the Laplace of a function which has been divided by t. From the definition of Laplace transform, we know that Laplace transform f of t is equal to 0 to infinity e power minus st f of t dt, and this is equal to f of s. Of course, the Laplace will be f of s. Integrating the above equation with respect to s, this is s. This equation with respect to s between the limits s tends to infinity, we get, okay. So look at this one, integration of f of s is to 0 to infinity sorry s to infinity, because the range is from s to infinity, so this is s to infinity, okay. Just take the integration of this and this, these are equal now. So integration s to infinity f of s ds and integration of this, so we have already we have to integrate this s to infinity, it will be cancelled, you can cancel these, and again we will have this this equation, okay. So we have taken integration s to infinity on both sides, and this 0 to infinity is from the definition. So now on the right hand side we have two integrals, so, okay. So you can see 0 to infinity and 0 to infinity e power minus st of t dt and ds. So this is we have taken this 0 s to infinity ds, okay, on both sides. Okay, so now we have to integrate this with respect to ds, so we have to change dt with ds, you can see, okay. And when we change this, this will be s to infinity and 0 to infinity. So we use the order of change of order of variables, change of order of variables, okay. So by doing the change of order of variable, you can check this in Google, that how what is the change of order of variables. So we can change the order of, because it is not easy just to bring this to here and dt outside of this deck, it is not easy. There is some rules, some formulas which you have to apply, though fortunately there is no change in the limits. You can see this 0 to infinity outside, and f of t and dt, because with respect to s they are common, sorry, they are constant. So 0 to infinity and f of t dt, we have take it out because they are constant with respect to ds, and we have entered this allow this this integral to enter s to infinity e power minus st ds, okay. But it is not easy just to change dt with ds. Now, okay, you can see here dt is inside the bracket and ds is outside, but now ds is inside the bracket and dt is out. So for this we have to use the formula, the procedure of the technique of the change of the order of variable, the change of order of variable. Okay, so you have to look at to go through this technique, that how we will change the order of variable. Okay, the order of integration, that ds should be inside and dt should be outside. So how to change this? This is not easy just to bring here and this ds to inside and dt outside. No, there is a procedure. Okay, and at some time it also changed the limit. Okay, so now you can see um, we have to integrate this with respect to s. So it is quite simple. E power minus st integral is e power minus st divided by minus t, and this is minus t. Okay, and this is bracket. Okay, actually, and the limits are from s to infinity. So you can see here uh, we can write f of t power by f of t divided by t, e power minus st, and when we apply the limits on this, so you will see the upper limit becomes e power minus infinity, and minus infinity is equal to 0 into okay, when we apply the limits, so it will becomes e power minus infinity minus uh, e power st, e power minus st. So minus infinity, e power minus infinity equal to 0, and e power st is equal to e power minus st. So there is no change. Okay, upper limit minus lower limit, this one. So minus into minus will become plus. So that's why we have f of t d, and minus e power minus st into minus, so it will become e power minus st. Okay. So now we have the first this integral has been solved, and now we have to solve the last integral, 0 to infinity f of t dt e power minus st dt, which is nothing. Look at, this is a function f of t e power minus, this is the Laplace, this is the definition of Laplace transform. So this is the Laplace of this function, Laplace of f of t s, which is equal to the left hand side, which is 0 s to infinity f of s ds. So this is, there should be this. Okay, write this here. Okay, s, right here, this integral s to infinity f of s ds is equal to Laplace f of t divided by ts. So when we have to find the Laplace of f of t divided by ts, so that will be equal to s to infinity f of s ds, integral of f of s ds, and limit will be from s to infinity. For example, we have, this is the function f of t, the whole function is f of t, the numerator will be the function of t, and it has been divided by t. So how to find the Laplace without using the definition and the complex procedure to find the Laplace of this? We will use a formula which have been proved, derived in the above example. Let f of t is equal to numerator 1 minus cos t, and the Laplace of f of t is equal to the Laplace of this left hand side and the Laplace of this right hand side. So the Laplace of f of t is equal to fs, the Laplace of 1 is 1 by s, and the Laplace of cos t is s square plus 1. So now we have, this is your f of s. So now you can see here we have to apply the formula. If we have the Laplace of f of t divided by t, so its Laplace can be found easily by this formula, s into s from the limit from s to infinity f of s ds. So this is your f of s. So Laplace of 1 minus cos t by t can be found as s to infinity f of s ds. So this is f of s, the value of f of s is 1 by s minus s by s square plus 1 ds. So you can solve this integral. It's quite easy. You can see here 1 by s ds. So the derivative of this is in the numerator. So we use the formula ln of s and limit from s to infinity minus, you can see the derivative of s square plus 1 is 2s ds. So just we needs only to multiply 2 here. So we will multiply 2 and divide 2. So minus 1 by 2, and then it becomes ln of s square plus 1. Okay. You can see now we have to apply the limits. Limits are from s to infinity, so we can uh, apply limits, okay, as a whole. Ln of s plus ln of s square plus 1 minus 1 over 2. I've just by using the power rule, okay, Laplace, so it becomes n power s square plus 1 minus 1 over 2. And you can see here ln of s plus ln of this. So we this is actually the product rule. So we can write this ln of s multiply s square plus 1 minus 1 over 2. And this is minus 1 by 2, the power is minus, so we can make it positive by shifting it to the denominator. So now it becomes ln of s by s square plus 1 1 by 2. And now apply the limits. So when you apply the limits, so you can see uh, sorry, before to apply the limit, because it becomes undetermined form is infinity by infinity. The look at here, when you apply the upper limits, it will become infinity by infinity form. Okay, so we uh, divide the denominator and numerator by s. So when we divide this by s, so it becomes 1, and we divide this by when we take it when take it inside the square root, so s will become a square. So s square divided by 1 is square. So s square and divide 1 is square. So s square will be cancelled, and just we have 1 by 1 by 1 plus s square. Now apply limits. So we have ln of uh, 1 plus 1 by infinity equal to 0. So ln of 1, which is equal to 0, and ln of 1 plus 1 by s square. Okay, because the lower limit is s. So ln of 1 plus 1 by infinity means ln of 1 minus ln of s square. So ln of 1 is 0. So we have minus ln of s by s square plus 1 1 by 2. And we can write this is minus ln of s square plus 1 by 2. So we can write this ln of s square plus 1 equal to minus 1 over 2. Okay, now look at this one. It becomes ln of s by s square plus 1 by 2 minus 1 whole minus 1. So how to make it positive? So it becomes ln of, it will be the denominator becomes numerator, and numerator becomes denominator, and the uh, power become positive. Okay, so it means ln of s by s square plus 1 by 2 minus 1. So it becomes 1 by s square plus 1. So the result will be this one. So how to apply this division by t? So the Laplace of 1 by cos t s, without using the definition, this is the Laplace of 1 by cos t by t. So when you have to keep this technique, okay, keep in mind this technique. You have to use this technique while finding the Laplace of a function when it is divided by t. Okay. Now we have to find the Laplace transform of periodic function. Okay, so first of all we have to define that what is a periodic function. So what is a periodic function? A function f of t is said to be a periodic function with period t. This is a period if f of t plus t equal to f of t. Okay, So you can see that if we add this, become the same function, okay, t plus t f of t. So we call this is a periodic function of period t. This is the period, okay, for all values of t and t greater than 0. For example, the trigonometric function sine t and cos t are periodic function of period 2 phi, okay. Sine theta plus 2 phi is equal to sine theta, and you can apply sine theta plus 2 phi is equal to sine theta, and you can apply the formula sine alpha sine beta plus cos alpha cos beta, sorry, sine alpha cos beta and cos alpha sine beta, and the result will be sine theta, okay. So and also periodic functions occurs very often in a variety of engineering problems. So you will see this is very periodic function play a vital role in science and engineering. So this is quite of importance, the periodic function, and maybe in circuits, okay, in signals we use sine function and cos function, so we needs a periodic function actually. So we must know that how to find the Laplace of the periodic function, okay. So we have this theorem: if f of t as a periodic function with period t, okay, if t is a periodic function with a period t, then the Laplace of f of t. Now this f of t is not a normal f of t. This f of t is a periodic function. This is different that from the other function we have defined previously, because it has the ability and it has this property. When we use something, for example, ft plus 12, it will give us f of t. So it is a periodic function, okay. So the Laplace of this periodic function and the period is t, ft plus t, its Laplace transform will be 0 to t, from 0 to its period, and e power minus st f of t dt divided by 1 minus e power minus st. Okay, this is actually a constant with respect to t, so you can take it out also, okay. You can write this here 1 by 1 minus e power st into this thing, because it is constant with respect to t, so no need to write inside the integral, so you can take it out. From the definition of Laplace transformation, we have Laplace of, now we are going to prove this, that the Laplace of the periodic function is of this form. So let me prove this, okay. So we use the proper definition, Laplace of f of t s, where if t is a periodic function, 0 to infinity e power minus st f of t dt, but this function is a periodic function of period t, so we have to divide this function into subintervals, that is 0 to t its period, and then from t to infinity, okay. So now if we substitute t is equal to u plus t in the second integral on the right hand side and write dt is equal to du, means if we take the derivative dt du and t is constant, so it will become 0, so d2 will be equal to du, okay. Now we are going to replace this t by u plus tau, and also where there is t, it will be replaced by tau plus u plus tau, and du will be equal, dt will be equal to du, okay. So substitute in the second integral t is as a u plus t, this will remain the same, and just we have replaced this, where there is t we have replaced this e power minus u plus t into s, because this is ts. If u plus t, this is u plus t, and dt is replaced by du. You can see here and look at the limit when t is equal to u plus t, and you can see here the limit is from t, the limit is t. So when the limit of, when t is equal to t, when the limit t is equal to t, then we put t is equal to t here, so the limit of u will become 0, okay. And if t is infinity, so u is also infinity. So now the limit has been changed from t to infinity, to 0 to infinity. Now this is 0, now not t, okay? This is 0 to infinity. And e power minus u plus t, it has been replaced by t. And it has been replaced by t. And dt replaced by du. Okay. And we have 0 to t e power minus st f of t dt plus as e power minus st e power minus s and capital T, this is constant with respect to u, okay? So now we have e power minus su, and it is a function of periodic of period t. So f of u plus t is equal to f of u, both are same, okay? E power f of u plus t, because this is the periodic function of period t, so f of u plus t is equal to f of u du. If you look at clearly, so you can see this is the Laplace transform definition: 0 to infinity e power minus s u f of u du, or f of e power minus st f of t dt, both are same, okay? Just if we replace this by t, because u is the dummy variable, so we can change this by e power minus st f of t dt, because du and dt are same, okay? So if you write here e power minus su f of u du, so again this is the definition of Laplace transform, but we just use the original variable t, okay, not. So Laplace of, what is this? This is the Laplace of f of t or f of u. F of t or f of u, both are same. So e power minus st Laplace of f of t is, this is the definition of Laplace. So just Laplace of f of t is. On the right hand side we have also Laplace of f of t. Yes, this is f of t. So look at this one. We just we shift this to the left hand side. This one. Look at here, and I have taken, because on the left hand side we have Laplace f of t s, and on the right hand side we have Laplace f of t s. So just take it common. Laplace f of t is common, and if you take this common, so we will have here 1 minus, and from this e power minus st. So the Laplace of f of t is, and shift this to the right hand side. This is in the product form, so on the right hand side it will be in the denominator. So you can see here the Laplace f of t, where t is a periodic function. The periodic function Laplace will be in this form: 0 to infinity. Sorry, this is not 0 to infinity, 0 to t. This is t, okay? So I have to top t. So let me write here t, okay? This t. So this is cancel, and we have here t. Okay, so this just will be replaced to t, and f of minus t of t dt. So it has been proof. We have proved this, that the Laplace of periodic function t is equal to this thing. So you can see we have proof. It was given in the theorem that the Laplace of periodic function t of period t is equal to this thing. So this has been proved. So now we have example. Find the Laplace transform of the periodic sawtooth wave function given by f of t by t of period t, and t is in between 0 and t. This is a sawtooth. Saw is just like you can see saw. Okay, saw is used to cut the wood. Okay. So you can see the graph of the periodic sawtooth function is defined, is described as, look at this one. This is just like the teeth of, this is why I call this sawtooth, the teeth of the saw. Okay, so you can see that when t is 0, so the function value is 0. When it becomes t, so it becomes value is 1. And after, you can see at 2t, its value is after a period of t, its value is 1. Okay, so this is the graph of the sawtooth function. Since f of t is a periodic with the period t, we have, this is the formula. Now no need to use this, the Laplace transform definition, but we have that the Laplace of the periodic function is 1 minus e power minus st, because now the period is t. If the period was 12, so there should be, instead of t, there should be 12. If the period is 3, so there should be 3. So now this is the period is t, so we have used this 1 minus e power minus st at 0 to t. This is the formula, e power minus st f of t. So now f of t is ta by t. You can see ta t by capital T. So this is the function 0 to t e power minus st ta t dt. So you can, because 1 by t is a constant, so we can take it out, and 0 to t e power minus st. So find the integral by parts. T integral of second minus integral of second derivative of first, and after using the limits, upper limit t e power minus st minus s minus lower limit, so t0 becomes 0 plus minus into minus plus 1 over s, and e power minus, the integral of this becomes e power minus st by minus s. Okay, so when we solve this, take it out, and the integral of e power minus st is minus e power minus st minus s, and then apply the limits. Okay, and this become plus minus minus 1 over square, upper limit e power minus st, and minus the upper limit, lower limit e power minus s0, so it becomes 1. Okay, so you can see we can take minus common from this, so it will become plus, you can see here, and apply this, multiply this to the bracket. Okay, multiply this, take it inside the bracket, multiply this, so this t will be cancelled with this t, and just we will have minus s e power minus st divided by 1 minus st, plus this minus plus, and 1 over s square t, and 1 minus e power minus st, and 1 minus e, because minus common, so when we take minus common, so it will become plus, and this will become 1 minus e power minus st. So 1 minus e power minus st and 1 minus e power st will be cancel each other, and just we will have uh, 1 by s square t. Okay, and in more visible form, or an appropriate form, I write like this: 1 by s square t minus e power minus st. This minus is now here. Okay, s1 by e power minus st. So the Laplace transform f of t 1 by s square, where t is ta by ta, small t by capital T, which is a periodic function, sawtooth function, and its Laplace is given here. Okay, so this is enough for the today's lecture for this week, for this week lecture, and you will have some weekly assignments. Okay, you have to solve those assignments. So I will just wind up my lecture here. If you have any problem and any question or confusion, so please feel free to contact me. I will always be available. Okay, for you. So don't worry or don't shy to ask. Okay.